Okay. Okay. I'm recording on YouTube. So one thing I want to say is to my subscribers, this is not a characteristic classes or research level presentation. It's on education. I'm happy to talk with anyone, especially academic mathematicians, about my work in mathematics education. And then secondly, I wanted to address this to the intended audience, which is folks who are in a session on education policy at the AMS. I'm sorry I can't meet with you, but have a pretty big family health matter to attend to. And whether you watch this, whenever you watch this, I deeply appreciate having your attention and hope that this can help spark a conversation. So what I wanted to share is at one level, a number of things that I've worked on, and you'll see that it's at all levels. Actually, I alluded to putting my graduate level courses on YouTube, but I've really worked from kindergarten through postdoc in a way, and then there's some coherence there, and that coherence is based on sort of some vision, and I wanted to share that. And in particular, eventually get to where I see the biggest work to be done, the most important work, and the biggest gap between where we are and where we need to be in the end of high school, beginning of college. So here's an outline. I'm going to talk about some efforts on our campus, some efforts in the state of Oregon. I'm going to talk a little bit about things that I've worked on and others have worked on in K-8 and what I see there, and then focus on grades 11 to 13, so to speak. Right. So I think I'll just fill in. University of Oregon's Math 101 is a credit-bearing replacement for remedial or developmental math. And it focuses on applications and really the skills that are not about just symbol manipulation, but actually skills about interpretation, finding uses for, finding equivalent forms for a purpose, that kind of thing. So let me jump right to, this was something that I developed with just on my own 2 trials in 2017, 2018. Then starting 2019, our department had a big development team, built on what I did and worked on it together. And it's now what we offer. And we no longer have any remedial, any non-credit bearing math on our campus, which you would think we should manage, but we actually had hundreds of students who were taking things and not earning college credit because, you know, they needed to faithfully take the cube root of a to the 18th and things like that. And that was holding up their college plans because they needed to learn again what to write when somebody asked them to take the cube root of a to the 18th. So what are we asking them for now? Well, here's from the final exam. This is not mine. This is, but I had some things like this. This is, you know, formula soup. You can see, if you've taught this population, you can hear the eyes glazing over almost. But now they're saying, well, here's this complicated function, let's use it. How much will it cost to have them work for 2.5 hours, right? That's a concrete question. One thing that could have happened in the interim, this final exam question isn't asking, is put this in words, right? Oh, for every hour between 2 and 12 hours, you're going to take, oh, that looks like a typo. It really should be H minus 2. Take the number of hours over 2 hours and then multiply that by 275. Wow, this problem has some flaws, but anyways, hopefully the students were graded generously. Then we've got this problem. What do the numbers 20 and 5,000 mean? Use context units and values. So 20 is a number of hours, right? It's this threshold over which you're looking at a different PACE system, and 5,000, its units will be dollars. It's this base amount for 20 hours. That's also, yeah, this is a problematic problem, but in any case, not mine. And again, what does 275 mean in this context? So that's the kind of work that we thought better matched what future scientists, future social scientists would need, ultimately coming into college algebra and then going out ultimately after college algebra, business calculus, stats to their science classes and their social science classes. So it feels like that has been a success. I took data in the really early initial pilots. Things are looking relatively good, but that's very superficial data supporting that at the moment, but well enough that we're sticking with it and instructors are seeing the value. So this work was inspired by some of my work with high school practitioners, high school teachers, high school teacher leaders. And back in 2014, I actually went to a education conference, NCTM affiliated conference, and some of our folks from the Department of Education were just sharing their vision of what high school math might look like if we ignored our legacy, Algebra 1, Geometry, Algebra 2, and they shared some of the research around the necessity of various things and just built it from scratch. And this is, that was 2014. As of 2021, this is the framework right now that Oregon schools are working under in terms of recommendations for math pathways. So it's called the 2+1 model because what we ultimately came to, and it resonates with the Math 101 work, we came to the idea that, Algebra 2 is not necessary for all our students' goals and aspirations, whereas Algebra 1 really is, and I'll show you what I mean by that in a bit. But and so let's really focus on what we aspire for all students. Histograms are something that I would want each and every citizen in our state, in our country, to have access to. So much so that I will make that a requirement. Whereas, I'd love for people to understand, say, sums of squares. That's a beautiful fact, but it has a very different, when I put my policy hat on, it feels very different to say require students be able to determine whether a prime, an odd prime is a sum of squares quickly, than it would to say be able to read a histogram and interpret that fruitfully. So, so this is a framework, basically cutting back geometry and putting some data science in there. But it's more than that for the first 2 years, and then have these options later. It's more than that, though, because algebra needs to look different. And one thing that that I worked on with some teachers and a few teachers in Baker City, around maybe a place or two else around the state, used this last year. They took lessons from Illustrative Mathematics. So Illustrative Mathematics is a group that now produces curricula. I worked with them when it was our job to illustrate the Common Core State Standards in Mathematics. It was started by Bill McCallum, who's one of the 3 lead writers of those standards. Bill's a number theorist. And Illustrative Math went on to produce curricula. And let me just pick a lesson, maybe equivalent equations. And it's a soup to nuts, openly available. Anyone in the world can use this. It's discourse based. You notice that they have some anticipated misconceptions for the teachers to look for. But it's meant to, you have problems for the students to work on. It's problem based and discourse based. And then the teacher's job is to kind of bring together and synthesize. And again, you see some of the flexibility, which expressions could be equal to P plus Q, right? So we used that curriculum to sort of say, all right, this is what we mean when we say linear models rather than linear functions, linear models. Here's the curriculum that really gives that modeling aspect, okay? And so you have basic linear functions, models, and systems, talk about functions at an abstract level, exponential next, inequalities, more talk about functions, including these piecewise functions like we did in Math 101, right? Piecewise functions are important. They occur in real world contexts. And then a bit of quadratic, but short of actually completing the square in the Oregon standards. So then what does it look like for students to really be proficient with this kind of algebra 1 that we're looking for? Well, here's a task. You're supposed to give out an $8,000 bonus split out among these people. How do you do it? Explain your method. I would put a question 3 here, which would be reasonable with an illustrative math. Give a spreadsheet make a spreadsheet so that if some of these numbers changed, if you had a 6th person who was on the team, who came in the team later, that you could actually get new numbers for it. That, by the way, would demand a real understanding of variables to use a spreadsheet in that way. In fact, I would love to have so much more spreadsheets in Algebra 1 with the right kinds of applications where you're seeing, in particular, oh, this is the value of having the value in the other sense of the word of having a variable. It lets us take whatever number is in that box and use it in different ways. And when that number changes, all of our different uses change. So here's the kind of activity that, again, rather than pure procedural, it's authentic. This is authentic application of mathematics. This is a problem that students can recognize, we can recognize, is something that people care to do in the world. Am I claiming that 15-year-olds are going to go gaga over this? No, but could they at least maybe grudgingly admit that this is sort of demanding something of them that is preparing them for their future? Yes. Okay, so that's the 2+1 model. And again, all these things I'd be happy to share more. Contact me. I'm easy, Dev Sinha, University of Oregon. You can find my email address. So the 2+1 standards are really focused on those 9th and 10th grades. The +1s I'll get to in a minute, but let me digress a little bit on K8. So K8's an area that I actually feel has been better developed in a lot of ways. Sorry, let me. Right. It's hard to get at the tabs sometimes. So here's a first grade task that I wrote with the help of a first grade teacher. Jasmine has 8 daisies and 3 vases. She puts 5 daisies in large, 2 in medium, 1 in the small. Can you find another way? Can you find as many as you can? Try to find as many as you can. Can you maybe even try to find them all? And how would you know? So as a first grade task, and again, first grade, normally they're asked 7 minus 2, 3 plus 5, right? Your number of facts. Obviously here you have to, this is developing number of facts, but flexibility, and again, an invitation to really sort of, you know, they're not going to have formal language, but certainly think through systematically in a way that is, again, authentic to what mathematics is really about. It's not so much fact recollection, although that's a piece of it, is in this case, it's fact recollection in the context of an interesting problem. It's also, by the way, this is an applied math problem, and it's ambiguous in, can you have no daisies in some vase or not? And of course, that changes the possibilities and can be a fun little discussion to have. But again, that's authentic to applied math, is often you are in some situation where you need to make an assumption or do some additional research in order to know what the actual constraints are to, quote unquote, make it a math problem. As you might imagine, I have a broader definition of what it means to be a math problem, because again, I want to emphasize applications, and here we see what that can look like in first grade. Now, what about, you might say, the joy of pure math? Well, illustrative math does have a lot of, they're called, are you ready for more? So little invitations to greater pure math. But something that I'm working on right now is for middle school, where our local middle school is working with us as we speak on lessons that can be done once a week. So illustrative math, you're learning your basic proportions, scaled copies, things like that. We all know that some students really need more. And what the recommendation is for teachers roughly once a week to engage their whole class at first in some juicier mathematics. And then students can, after they've done a little bit of it, they can choose, some might choose to actually review what they've been working on, maybe shore up some poor performances earlier, fill in some assignments or something like that. Some might choose to, I don't know, do Dreambox or some software, and others could continue to dig in. So this is about the Sierpinski triangle. Students have been looking at scaled copies of things, but now can you find 3 scaled copies of the Sierpinski triangle that cover it, or more, some different number? Can you find 5? And so it goes further, looking at these different fractals. Oh, can you think of a fern in that same way? And then you get to problems like, these are my favorites. The spiral you can cover with just 2 copies, but the Sierpinski triangle, Jamil and Yolanda both see 3 scaled copies. Jamil argues that each is a quarter of the area because you scaled half in both ways. And Yolanda found the same copies, but because there's 3 of them and they're all the same, they each must have 1/3 of the total area. Whose reasoning is sound, right? So that's kind of a fun one. Both, of course, because the area is 0, and we're giving students who could really have that insight and really love to go deep to do that. And this would just be in the regular classroom, but they have that invitation to go much further if they're ready for it. So in fact, I kind of envision, because there is some controversy around things like separating students, and especially around acceleration. But I would start saying, maybe in 5th grade, you start having these invitations for more, the lessons. And it's really invitations for much more. And then maybe starting, and so students, maybe 4th or 5th grade. And then you get a sense for the ones who might consistently really dig in further. So maybe even starting in 6th or 7th grade. I would propose an acceleration where students who have not only done the basic lesson, have not only done well on some of these more interesting problems that illustrative math does, but also find the invitations to much more really compelling and do well on those. Maybe they do art of problem solving over the summer. Maybe districts even make some investments so that can happen for some of their students. So it doesn't become an issue of resources. Our current system, I think there's some contentious debates, but I think the data is clear that the parent advocacy is too much of a variable, and SES becomes too much of a variable as to who has access to deeper stuff. And so I think we can all get on the same page that maybe let's think about systems where everyone can start to engage, and based not on just compliance. That to me is not authentic mathematics. That really is primarily about compliance and recall, but about problem solving, communication, insight, and passion. That the kind of mathematics that then can say this student is ready for more. And if you accelerated through every year, maybe between 6th and 7th, you do 7th grade math. and then you're in a regular 8th grade classroom in 7th grade, et cetera, you can be, like me, a kid who takes calculus early in high school, but unlike me, I think you would have felt, I felt a lot of depth was missing. I really look forward to graduate classes to finally understanding why. You don't really need that. You just need deeper experiences in what you're studying. You don't really need to wait until graduate school to understand why. So that's my digression, and you have the basal curriculum that's engaging, but to also, starting in 4th or 5th grade, some invitations for more, and after that, have things like acceleration based more on some of this problem solving and less on parent advocacy. Okay, so let's get back then to grades 11 through 13. And I mainly wanted to say these are where we need to, these are our biggest, this is the biggest problem area, problem time. If you look at success rates, if you look at students who want to do X, but either avoid some pathway because of the math, or just are delayed or unsuccessful, then this is where we need to do a lot of work. And so let me give a couple proposals, but let me actually back up and say that part of the need is to really think about what it means to do and to teach applied mathematics. And we've seen a little bit of that with the high school task with spreadsheets. We've seen a little bit of that even with daisies and vases. But that's a big sub problem is we need to get good at teaching applied math, and that even means understanding what it means to do applied math. So let me digress again a little bit and just say my personal model. I need to maybe bone up on some philosophy of or ontology of science and applied math or something like that. But the way I see applied math is, you often have some data exploration, and there's going to be cycles in here, and then you have model building and interpretation and connecting, but I think it really, that can be part of the building. And then finally, you have evaluation, thinking about things like inference and error. And you have all these different pieces, and the most mathy of those is the middle piece, right? That's where, and first of all, what do I mean by a model? A model, I think it should be understood that even saying a number like average income, there's implicitly a model there, right? There's a, you don't have to go much further to say that something like well, if you want to say typical income, then that would actually be median. So the median for the incomes in the United States is whatever it is, 60,000-ish. And so you should, so even single numbers can be models, but functions can give models. What does it mean to model with a function? Well, you can take a real world function, something like measurement of temperature at a particular location, or distance of a rover away from the Earth, or whatever. Those are ways to produce numbers in the physical world. And you're saying that this mathematical way to produce numbers, like take this number, square it, and add it to some other number, that agrees well with this real world function. So even understanding this fact that, and maybe mathematicians might not want to even call real world functions functions, but I think it would be powerful to start calling this out as to what we're doing when we're doing modeling. And again, this is probably where quote, more math is. And if you look at the other two ends, maybe one is data science and one is stats. Although I think that, and by the way, it's important to understand this distinction. One of the problems in social sciences, the reproducibility crisis in psychology and other social sciences, were because if you allow yourself to data explore and evaluate at the same time, you can p-value hack and things like that. So there's some value even at the edge of science in being clear what we're doing when we're doing applied mathematics. But for me, that's just also being authentic. Let's have our curricula sort of have these in mind. So what are some of the options? Well, here's one system. Here's the minimal system. In Oregon, there's often, I think I might have to switch to typing. In Oregon, we've got a number of one building schools, one teacher high schools. And so this is the minimal system. You have an algebra 2 pre-calc discrete option and a math modeling with the data option. So 2 classes beyond the first 2 years. Probably students will see the math modeling with data is more accessible. The algebra 2 pre-calc discrete is roughly, let me say, it's roughly comparable to college algebra and pre-calc. For us, those are Math 111. But those are numbered Math 111, 112. People would say, well, you expect students to be able to do that? Well, grade 11, grade 13, there's actually not a huge difference other than selection. And so if you have an option that students are opting in for, because algebra 2 is problematic, look at the data, and students often take algebra 2, 1, 2, and then do some remedial math and take college algebra, and they see the same stuff, and pre-calculus, they might see the same stuff 5 times and they're not getting it. So why should we expect students in 11th grade to do this? Well, first of all, one of the main things is that they're opting in. And this is, of course, going to be a key thing for a STEM pathway. You want to have this material. And then what we do in college in like 40 meeting times or 80 meeting times, high schools have much more than that. I add discrete math in here because discrete math is a huge block for computer science and that kind of pathway. And when we teach algebra 2, there's just so much with binomial theorem and things like that, that we really ought to integrate that as well to prepare students, if they want, to keep that door open for doing some more serious computer science or just study of computers. And then you have math modeling with data, which, if you look at quote unquote the math, it sort of expands the function types. Maybe you look more at rational functions, which are important if you're doing different like mixing of fertilizers or things like that. But you also emphasize, as I said, some integrating the data science and the evaluation there. And look, even thinking about numbers fruitfully is so important. And again, students come out of their high school and even college experiences saying, okay, I know how to FOIL. Whereas if you say, well, you're cutting something and it's supposed to be square root of 31 inches, what is that going to be to the nearest 16th, right? And they have no tools for doing this. Teachers struggle with that task. I've given teachers that task because our system doesn't have anything about demanding some flexibility with numbers. But if you're doing some actual evaluation and inference, and you want to say, okay, we're going to cut this to the nearest 16th, and you want to know how far you are away. Well, A, you're probably at most a 32nd, but B, there we go. Let's find the nearest 16th. So that's one system. There you could split the math modeling and the data in two classes. So that would be another system if you had more teachers, and then and you see that out there. Some high schools are already implementing a math modeling class and a data science class, and I think that's fine. This is in our standard way of thinking of it in terms of math content. I would love to also see students play with things like this can be expand. Maybe things like data science and math modeling. Two year-long courses. The other thing that you could do, and again, this is just I'm not seeing anyone implement any of these yet, would be, start integrating with interest areas. Things like math and government, say, where you're using math to understand government policy. And you have to be careful. You want to make sure students are really extending themselves as learners of mathematics, but math and CS, math and government, maybe a number theory class. Hey, why not? Let students see math for math's sake. The students who, starting in 5th grade or whatever, love those fractals, love the base BMLs and like base 2mls, 0.1010, things like that. Loved all that stuff. Maybe they're ready for a real pure math class in high school. Wouldn't that be wonderful? There are some that are equipped for that. Let's let them run with that. Yeah. So I'd love to just see people develop these, share them, and try them. But one of the main things is that I really feel like we need to work together and also be developing similar things at college. And so I would want to I would also want to see us look at the beginnings of college and explore the idea that we have, rather than one size fits all college algebra, that we have pathways that can feed into various things. College algebra can feed into life science, business science, hard science. Let's have versions of just math for life science that might have more discrete math or more emphasis on exponentials than the social science kind. Let's think about something that would feed into our math for computer science, discrete math, and actually have students start to get ready to that proof thinking. We spend so much time in bridge courses for majors, but there's a bridge need for computer scientists, and there's a real equity problem. Historically excluded learners on our campus are not doing well in our 200 level class. So I would love to see a 100 level class, an entry level class at the level of college algebra, but that really got you thinking about discrete math, playing with graphs and permutations, combinations, and things like that at an appropriate level so that students could then start succeeding further into computer science. Let's prepare students for stats and not like have to cram in histograms very quickly and feel like you have students who don't even know what a histogram is, and at the end of 10 weeks or whatever, they have to be calculating and interpreting p-values. Let's really sort of, I would love to just basically take our 200 level math. You could look at, say, how Harvard's quantitative reasoning, as that's all 200 level for us. That's calculus and comparable to calculus. And think about our entering systems for the students who need it to be ready. Yes, some algebra intensive things for the calculus for STEM, but other experiences for the life sciences, social sciences, etc. Look, the vision is that one day we don't need those 100-level classes anymore because high schools have gotten it right with our help. But I don't think high schools can really do some of this work at grades 13, 12, 11, and 12 without us really thinking about grades 13 and 14. So that's part of the vision and the work that I'm most excited about right now. Okay, I'm going to call that a day, and thank you.